Illustrative Math, Algebra 2, Unit 5, Lesson 9 is called Scaling the Inputs. All right, so our goal today, I can describe the effect of a scale factor on the input of a function, and I understand the difference between scaling the outputs and scaling the inputs of a function. Okay, so this stuff here, vertical shrinking, horizontal shrinking, that was from the previous lesson. That was, what was that? What are we on here? 5.9. So that was 5.8. So if you didn't watch my 5.8 video, you might want to go back and watch that to learn how to do vertical shrinking and stretching. This is what we're going to do today. This is for 5.9. All right. So if you notice here on a vertical, your constant. I use C for constant. You put that number. You multiply the entire function by C. Okay. So f of x times C, and then this is going to be f of C times x. So here's the difference though. If I want to stretch, C is going to be between 0 and 1. It's like the opposite of what you would think. So let's give an example here. Let's say I want to stretch by a factor of 6. Okay, this has to be greater than 1 if I'm going to stretch it. The problem is with my function here, I need to plug in a number of C that's between 0 and 1. So it's really going to be f of 1/6 of x. I plug that into my function. So if my function was, let's just say x squared, I'm going to plug in 1/6 in for x, and squared, I end up with 1 over 36 x squared as my new function. I'll call it g of x. Okay. So that's what happens there if the number is on the input. Okay, so it's actually going to be the reciprocal of what you would think. So when I look at this, I see 1/6. I think, oh, it's probably going to be a vertical or horizontal shrinking because 1/6 is less than 1. But if you look here, if it's between 0 and 1, it's actually going to be a stretch. So you got to flip it to get your function there, your scale factor. Okay, so if you notice here in the table, it's the reciprocal of C is what you're multiplying the x coordinates by. So that's where I get the flipping from, okay? All right, every weekend, Elena takes a walk along the straight road in front of her house for 2 miles, then turns around and comes back home. Let's assume Elena walks at a constant speed. Here's a graph of the function f that gives her distance f of t in miles from her home as a function of time if she walks 2 miles per hour. So your distance gets further, and then she turns around and comes home, and your distance gets back to 0 when she's back home. So number 1, sketch a graph of the function g that gives her distance in miles, g of t in miles from home as a function of time. She walks at 4 miles per hour. So this was 2 miles per hour. Now we're going 4. So we're going double the speed. So just right up here, double the speed. Should shorten the time in half, okay? So if I were to think of it like this, if this were my function here, and I'm going to kind of trace it there. If I were to cut my time in half, right there, be like, oh, the whole trip went from 2 hours to 1, but you still get the same distance away. Your slope is just steeper because you're moving at your rate of change is greater. You're at a faster pace that you're walking. Your graph's going to look something like that. So over here, I'm going to sketch my graph just like that. It's only going to take me half an hour to get to the end point, and then I get home in 1 hour. So the graph would look something like that. So we'll call that G over here. Now write an equation. So what happened here with my graph was it went this way, right? It was a horizontal compression because I squished it towards the y-axis. So we're going to call this a horizontal compression or shrink. I think I use shrink in my table by 1/2. Okay, so what I need to do is I need to find f of the reciprocal. It'd be 2, I'm sorry, not 2c, 2x. C is 2. I keep trying to click on that eraser. C is 2, so it'd be 2x, okay? So let's make sure I use the right notation. The original was f. So, instead of x, I need to use t. So that's going to equal my new function g of t. I don't think they gave us anything else, so there it is, okay? And if you go back there and look, that horizontal shrinking, c has to be greater than 1. But we saw everything is half the distance towards the y-axis, so c is going to be the reciprocal, or the reciprocal of 1/2 is going to be my c. All right. So a couple units ago, I don't remember which section was 5.4 maybe. We had a problem with Claire on a Ferris wheel, and we have a function here that gives her height above the ground. Height above the ground in feet, t seconds after starting her descent from the top. So she starts at the top, and then she eventually gets down to the ground after 80 seconds. So your picture would look something like this. I need a circle. So if this is your Ferris wheel, it's kind of like here's the ground. Sorry. Right here. It's kind of like, okay, up here at the top, at time 0, they start the clock, they say go. This is halfway. This would be 40. And her height is 106. And then down here at 0, or I'm sorry, the height is 0, but it took her 80 seconds to get there. That's supposed to be a comma. And then here, these would be halfway. Your height here would be 20 seconds because she's moving this way. 20 seconds would be at 181. And then this would be 60 seconds. She's down here at 31. So it'd be some sort of situation like that where she goes from the top all the way down here. All right. The first wheel is twice the height of f and rotates at the same speed. Function g gives Claire's height in feet t seconds after starting her descent from the top. The second wheel is the same height as f, but rotates at half the speed. Okay. So the first one, if it's twice the height, the only thing that's going to change is the y-coordinate here. So if I go ahead and double all these, 424, 362, 212, 62, and then 0. This is really 2 times f of t, essentially. All right, now if this one's going twice the speed, okay, at time 0, it's still at 212, but at 20 seconds, really, Claire's going to be at the same height that she would have had at 10 seconds. But the problem is we don't have that data, so I don't think we can fill that in. But 40 seconds, she's going so much faster that whatever her height was at 20 seconds, which was right here, that's going to go right there because she's going so much faster. The next one here, 60 seconds, we would need to know what her height was at 30, which obviously is between these two numbers. I just don't know what it is exactly, so I can't really fill that in accurately. 80 would be the same number that she got in 40 seconds. So that would go right here. That'd be 106, okay? It's going half the speed. I'm not sure if I accidentally said double the speed, but it's going half the speed. So that's why 20 seconds took her longer to go. I think I might have said that backwards now that I think about it. So 20 seconds took her 40 seconds to get the same height. So this one was twice as fast. F of t was twice as fast. This was twice as this was half the speed. So this took twice as long, I guess. So 40 seconds took you 80 seconds. So if you think about it, your graph is getting stretched horizontally. So this is going to be, because it's taking so much longer, this is going to be f of 1/2 t, because it's the reciprocal. So 1/2 is the number you plug in your function, but you really need to flip it to get that scale factor of 2. All right, so I guess why is there not enough info? I guess I kind of mentioned it. I would say to find h of 20, we would need f of 10. And then to find h of 60, we would need f of 30, which we do not have either. Okay, so we already did these for both of these. Okay, so express g and h. I guess I kind of did on top there. So I guess g, I'll write it again down here. So you have it g of t is equal to 2 times f of t. H of t is equal to 1/2. Or I'm sorry, f of 1/2 of t. All right. Function k is a transformation of function p due to a scale factor. Write an equation for k in terms of p. So let's see, k is here. K is a transformation of p. So we're basically going this way. We're going from here to there. Same thing here. You're going that way. You're getting, so if we're going from, how do I know I'm not going horizontally? Because the x coordinate here doesn't change. If I was going horizontally, this would move, but since it doesn't, it's definitely going vertically. So write an equation for k in terms of p. So p is, and I'm going to highlight those so you can see them here. Here's p. Here's k, because you couldn't really tell. So k is a transformation of p. So it looks like it's a vertical stretch. So if I look here, this is -1, I go to -3. If I look at the y coordinate here, so like this point, the x coordinate is -3, but what's important is the y coordinate for the same x goes from -1 to -3. So it looks like I multiplied by 3. So k of x is equal to 3 times p of x. So on the same axis, graph the function m, where m of x is p of 0.75x. How about I do this? I'm going to rewrite it as m of x equals p of 3/4 x. So when I change the input, my actual horizontal stretch or shrinking factor is the reciprocal of this. So it's a horizontal stretch by 4/3. So basically, I'm going to take my x's and multiply them by 4/3. So for number 2, I'm going to come over here. I'm going to make a table because I told you what to do. So I'm going to take all my points here, and let me do this. Let me clear all this stuff off of here so you can see it a little bit better. And let's do this. Let's get the kind of the important points from our graph here on P. I'm going to that point, these 4 points. So let's write them down here. So I got -3, -1. I have -1, -2, 0, 0. I have -1, 2, and then 4, 0. So what I'm going to do here is I'm going to multiply all these x's by 4/3. That's supposed to be a 3. So I'm going to make my new table over here in red. So the y's don't change. This is going to be -4. This is going to be -4/3, -2. This is going to be still 0, 0. This is going to be, oh shoot, this was supposed to be, sorry, that's supposed to be a +1, sorry. This is going to be +4/3, 2, and then this is going to be 16/3, 0. So I'm going to plot these points here. I'm going to kind of clear all this off of here, and then I'll connect them, and we'll see what it looks like. So -4, -1, -4/3, -2. So that's like -1 1/3. I want to make it a mixed number. This is 1 1/3. So I go to the right 1. Actually, put the 0, 0 here. Go to the right 1 1/3 up to, and then 16/3. That's like 5 1/3. So I'm going to go all the way over here. And I'm going to connect the dots here. I'll use red since that's what my table was in. So it looks like I go here, 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 and then right there. Okay, so definitely got a little bit wider. All right, the highest point on the graph of P is 1, 2. What is the highest point on the graph of N, where N is P of 5x? Explain or show. So this is going to be a horizontal shrink by 1/5. So nothing's going to change vertically. So it's going to have the same y coordinate. I just multiply that x coordinate by 1/5. So it's basically going to look like this. The 1, you're going to multiply that times 1/5. The y coordinate will stay the same. So it's going to be 1/5, 2. Furthest point to the right on the graph of P is 4, 0. The point furthest to the right on the graph of Q is 18, 0. Write a possible equation for Q in terms of P. So if I took 4, times it by some number, that'll give me 18. So if I divide each side by 4, I'm going to get C equals 9/2. So that would mean that it got horizontally stretched by 9/2. So what I'd have to do is, in my function, I'd have to plug in 2/9 to my function. So my Q function, Q of x, is going to be P of 2/9 to change the input to 2/9. That way it'll produce a horizontal stretch by a factor of 9/2. All right, so here's my function here. I guess we're going to figure out what the transformation was. So since this is the same function here for this first one, x plus 3, x minus 2, but the numbers on the outside, you're scaling the outside, this is going to be vertical stretch by a factor of 4. Okay, on this one here, because you changed your inputs, we changed our input to, let's think of it as 1/2 x. Change this to a 1/2 x. Change this to a 1/2 x. It's going to be the reciprocal of that to determine the scale factor. So I'm going to say this is a horizontal stretch by a factor of 2. Okay, this one, you changed your inputs, you multiplied by 3. So this one is going to be horizontal, and this time it's a shrink or compression by a factor of 1/3. It's the reciprocal. When you change the input, we change the x to 3x. Okay, and then the -5 on the outside means it's a vertical shift or translation down 5. Okay, that was from a previous lesson. All right, so I can goals here where I can describe the effect of a scale factor on the input of a function. So input, just remember, if you're stretching it, your stretch factor is going to be greater than 1, so you'd have to plug in the reciprocal, which would make it now between 0 and 1. And if it's a compression, your scale factor is between 0 and 1, but when you flip it, it'll make it greater than 1 when you plug in the input. Scaling the output, scaling the inputs. Go back to your table on the front and take a look at that if you need a refresher on that. All right, last one here. Here's my graph. Here's my function. Priya wants to transform the graph of f by stretching it horizontally by a factor of 5. She says an equation for a new function p in terms of f is p of x equals 5x, which means p of x equals 5x squared plus 3. Is she correct or not? So she would not be correct. No, she is incorrect. She would need to change the input to the reciprocal of her stretch factor. So 1/5. Okay, so what it's really going to be is going to be p of x equals 1/5 x squared plus 3, which if you wanted to simplify it, it would end up coming out to be 1/25x squared plus 3 would be your p of x. Or I guess if I wanted to rewrite this one, it would be p of x equals 1/5 x, would be f of 1/5 x, which would then make it what I had here originally. Okay, so hope you enjoyed this lesson. Thanks for watching, and we'll see you next time.